announcement. So we have a new website where you can find all the information about the series and the link for the next seminars. Also, we have a YouTube channel where you can find the previous recordings. They are organized, divided by year or by topic. You can search for what you want to hear. And I will post the link in the chat window as soon as the seminar starts. So now coming to our guest, today is my pleasure to introduce Asif Equbal. So I read his CV, and he trained in some of the top laboratories for magnetic resonance. So he did his master thesis with Matthias Ernst in ETH Zurich. Then he moved to Aarhus in the lab of Niels Christian Nielsen, where he did his PhD, working on heteronuclear spin decoupling in solid-state MAS NMR. Then he went to Santa Barbara with Song Yan for a postdoc, where he started working on the DNP mechanism in solid state, and this is why his name is most known for. After that, he moved to Northwestern again with another big name in EPR, Professor Basilevsky. And then after that, he got a position as an assistant professor at NYU in Abu Dhabi, where he started just a couple of months ago. So today, Asif is going to talk about how to use an EPR to disentangle different DNP mechanism in the solid state. And yeah, if you have any questions, you can write it in the chat during the talk or after the talk. And then, yeah, Asif, it's yours. The floor is yours.
Thank you, Thomas. And thank you all the organizers. I think organizing these Zoom platform series, it's a really challenging task to organize speakers and to maintain it, keep it running. So yeah, you guys are doing great. But I am sure it's very satisfying to be able to help community remain connected. So today I will be talking about how EPR can help us to distinguish single electron and multi-electron DNP mechanisms. And I know like some of you may not be an active researcher in DNP. So I will first start with a few basic questions like what is DNP, how does it work, and how can EPR actually help to develop DNP? I'm sure you all would agree that for any spectroscopy technique, we need two key factors. One is resolution and the other one is sensitivity. And normally it's hard to have both, the best of both resolution and sensitivity for a given spectroscopic technique. It's related to Boltzmann factor, it's related to uncertainty principle. Sensitivity, for example, is related to energy difference that we probe. If the energy difference is larger, then we have larger population difference and more sensitivity, and vice versa. And resolution is also related to energy. If high energy is there, then the uncertainty is larger, and then resolution becomes poor. So these two things, normally they go in opposite direction. In the case of NMR, we are able to get high resolution. And for solids, we have high resolution by going to higher magnetic field and faster spinning frequency. But we lack sensitivity in NMR because we probe a very small difference, energy difference. EPR, on the other hand, is opposite. We have this energy difference in EPR is 3 orders of magnitude larger than NMR. So we have high sensitivity, but we lack resolution in EPR. And these two techniques, NMR and EPR, they are very similar. The difference only comes in the time scale, and that's because the energy in EPR is larger. So, and that in turn is because of gyromagnetic ratio of electron spin is 3 orders of magnitude larger than that of nuclear spin. So the idea with DNP is to combine the best of EPR to have the sensitivity of EPR, but to maintain the high resolution of NMR. So in nutshell, DNP is a technique which can transfer high electron spin polarization to the nuclear spin. It is possible if the two spins, they are coupled, and we know there is something called hyperfine coupling. So these two states spins can be coupled, and with the help of microwave, it's possible to improve the NMR sensitivity. And DNP already has a lot of applications. We are now able to probe nuclear spins, which were practically impossible before DNP. And in the future, if DNP is developed, we can do hyperpolarized biomedical imaging. And that would be really revolutionary. Right now, one MRI scan may take hours. With DNP, it will be just in a minute. So it has huge scope for future development in many directions. At present, DNP is mostly being used for solid state NMR, and it's basically an add-on tool to solid state NMR. So assume this is your solid state NMR. We have a magnet, we have a probe or resonator, NMR console. To that, we need two more components to make DNP work. One of them is a cooling unit, because the DNP experiments, they are performed at lower temperature, much lower than room temperature. And then we need a source of microwave. And if we zoom into this probe, we have a rotor, which is basically a sample cup, which can also spin. And in that, we have the target molecule that we want to study, along with a polarizing agent. At the moment, the most conventional approach is to have them separated, not coupled, through some chemical linker, and it helps to have a better resolution, to maintain the resolution for NMR. What is one of the most important research topic at the moment is to have a better polarizing agent, most efficient polarizing agent. And these polarizing agents, they determine the overall efficiency of DNP. They can be different depending on what kind of DNP mechanism we are targeting. If you are targeting and something like Overhauser DNP, then we need basically single electron spins, and they can do the DNP enhancement. Here, what we do is, if you have this EPR line for the single electron, to saturate that. Once electron spins are saturated, they try to come back to the Boltzmann equilibrium, and there could be a pathway through cross relaxation of both electron and the nucleus. In that process, the nucleus spins, the signal of nucleus spins, that gets amplified. So through either zero quantum or double quantum cross relaxation involving electron and the proton. But such mechanism would be very much dependent on the intrinsic dynamics of the polarizing agent. So it's something which is one cannot very well control. What we can control is a mechanism called solid effect. Here we do something similar, but then we drive those zero quantum and double quantum transition through microwave. And this is very much in our control, how we do it. So if we have this EPR line, we drive the transition at an offset, which is equal to nuclear Lama frequency. At positive or negative offset, we get positive or negative TNT. The third, but there is a problem with solid effect, for which we need some other mechanism. And problem with solid effect is these transitions, they are normally, the transition moment integral for these transition is very low with microwave. So you need more and more microwave power in order to have a better effective transition. And that's something which becomes more and more challenging as we go to higher magnetic field. And higher magnetic field is important to maintain resolution. So at condition where we'll have high resolution, solid effect is not efficient. So we need another mechanism, which is the most popular one is cross effect. It requires two electrons, but at a certain condition. And the condition is that the energy difference between the two electrons, that has to match the energy of the nuclear spin. If we do that, and if we saturate one of the electrons, then through cross relaxation again, or relaxation of all the three spins together, the nuclear population, the nuclear polarization gets enhanced. So if we have 2 electrons, if we saturate any of these, we get either positive or negative DNP. So this is the basic of cross effect. Normally, so these 3 concepts are well understood. Normally, when we do DNP experiment and we get a DNP profile, people try to deconvolute the DNP spectrum as a sum combination of these things. Sometimes it might be right for simple cases like tempo based DNP. It may be right, but then if we go to a more challenging polarizing agent or some intrinsic polarizing agent in some crystal, then it can be misleading. So I will highlight you 3 cases, 3 very recent cases where people got very surprising DNP effects, something that was not expected based on the understanding of the 3 mechanisms. The most recent one is a work by Daphna Shimon, and in her experiment on P1 centers in diamond, other than expected solid effect, she sees enhancement right at the center of the P1 center. So this negative is something which is really unexpected. And there are other enhancement also which cannot be just from a single P1 center. It has to be many P1 centers coupled. Only then these effects can happen. So this is something which is surprising. Even for the case of organic radicals like trittle and BDPA, there is some enhancement in the center, and these enhancements which have encircled, they are not expected. What is only expected is the solid effect. So just to elaborate, trittle is a narrow line radical, so it has a very small G anisotropy, and the EPR line is much narrower than proton Lambda frequency. In such cases, one would only expect the 0 quantum or double quantum solid effect. But if you go to higher concentration of trittle, like from 5 millimolar, if you go to 10 millimolar, and then even further to 40 millimolar, we start seeing something in the center. So this effect can only be validated if we assume that there are many electrons participating in the DNP of trittle. The more interesting case is that of BDPA. So in BDPA, like trittle is also narrow line radical, in fact, narrower than trittle. And what was expected is just solid effect, but we also see some additional enhancement in the center. Initially, this central enhancement was attributed to Overhauser effect. So it was assumed that since there is a resonance structure, the electron spin, the unpaired electron spin hops, and that hopping of unpaired electron, it fluctuates the hyperfine coupling. So that was the assumption that people made initially. And to validate this assumption, 2 cases of BDPA were studied. One where the BDPA is fully protonated, and the other where it's partially deuterated. If it is fully protonated, we get a positive DNP in the center. And if it is deuterated, especially at the position where hyperfine coupling is strong, then the DNP enhancement in the center becomes negative. And it was the reason for this was attributed to dominance of 0 quantum cross relaxation if it is protonated, or double quantum cross relaxation if it is deuterated. So this was the reason that was attributed. It makes sense, but then this is not the only possible explanation why we can have a positive or negative enhancement at the center. It is possible, very much possible, that if these 2 electrons in the BDPA here in the protonated and deuterated, if they have different relaxation rate, which most likely they will have because we are changing the nuclear spin around the electron center. So the flip-flop of nuclear spin, that rate and what nuclear spin is flip-flopping, that changes. So it can change the T1E of the electron. If that changes, then an alternate pathway is possible. It could be that the mechanism is not Overhauser, but it's multi-electron spin-based cross effect, or what people normally call it to be thermal mixing effect. So depending on what T1E we assume for a coupled BDPA, multi-coupled BDPA, we can have a positive, negative, or dispersive enhancement in the center. And so the positive and negative is already seen here. And very recently, just a year ago, Thomas Prisner's group, they saw something very surprising for the BDPA. They see that BDPA, when it is dispersed in lipid, it gives a dispersive enhancement profile in the center. So now we have positive, negative, dispersive, and this is theoretically predicted, numerically predicted, that yes, for multi-coupled electron spins, we can have positive, negative, and dispersive, depending on what relaxation we have. So, but then someone can have an argument that in BDPA, it should be each molecule, individual molecule of BDPA should give you just positive and negative. But then if it is put in a condition that it cannot dissolve well, so these experiments are done in polystyrene, and if you don't control your matrix of polystyrene, it may happen that BDPA are getting clustered. So that can be a strong argument. So to solve that riddle, recently we have done these same experiments, DNP experiments, involving BDPA, but a different form of BDPA, a sulfonated BDPA. Such BDPA molecules are water soluble. So if we put them in a glassing matrix, it will be all dispersed. Here also, we see that the DNP profile is, in fact, there is a DNP enhancement right in the center of BDPA, and the enhancement changes, the profile changes with temperature, and the profile can take any shape. It can be absorptive at higher temperature and dispersive at lower temperature. So the central feature is not necessarily it's coming from Overhauser, but it could be because of the intrinsic nature of BDPA, that it may happen that the BDPA in a real scenario, it's not isolated, but two of them or three of the BDPA molecules, they're stacked. Even in solution, they are stacked. So this is a possibility. But how do we test that possibility? How do we test that our assumption is not necessarily true? In reality, we may have clustered electron spins. To prove this, we need to go to EPR. And proving this is very important because the DNP mechanism of two monoradical would be very different from a single biradical. So we need to know about the coupling network of the electron spin in order to bifurcate whether the DNP is from multi-electron or from single electron. EPR is already very advanced, but most of the experiments that have been designed in EPR, they work at very low concentration. Normally, the concentration is less than 1 millimolar. And DNP is performed typically at very high concentration, at 30, 40 millimolar, maybe sometimes higher than that. In EPR, there is a technique, DER spectroscopy, which is very popular, and it can measure distance between two electrons, but then it cannot be really used for DNP because the distance ruler for DER is like between 2 nanometer to 7 nanometer. What we are talking about more closer distance, like angstrom, 5 or 6 angstrom, whether or not two electrons are at that distance, DER cannot be used, in my opinion. Also, when we do pulsed EPR experiment at low field, they cannot really corroborate DNP experiments which are done at high field, because in low field, the ratio of coupling and magnetic field is different from that at a high field. So something which is non-secular at low field becomes secular at a higher field. There are other kind of experiment where one can do ADRF, adiabatic sweep of microwave, and convert Zeeman order into dipolar order, and those kind of experiment would be an indication of coupling network, but it requires very high microwave power. So we cannot really use the existing experiments to have some insight about the electron spins for the case of DNP. We need something different. And so what we are doing what I did in my postdoc lab, and that's being continued, and a few other labs are also doing, is pump probe experiment. So the idea is very simple. Suppose I have this chain and there is like this black box. I do not know in this box whether or not the chain is still connected. So what you can do is you can perturb at one end and see if that perturbation at one end changes anything on the other end. So perturb here and probe here. If there is a change, then most likely they remain connected. Otherwise, they are not connected. So we do something similar for the EPR line. We have an EPR line, and to know whether or not two spin packets are connected through dipolar coupling, we pump at one frequency and probe at some other frequency. If by pumping here, the intensity at the probe frequency changes, then we know there is some connection. Only then it will change. So we do simple experiment, pump probe. It's little hard to execute because to do these experiments, you need either two microwave source or you need an AWG to split, to change the frequency. So, but in Songi Han's lab, the setup is already well developed by many people in the past, including Ilya Kaminkar, Alisa, and many others. So this is very well established. The way we do this experiment is, suppose you have an EPR line and you choose a particular frequency in this EPR line. Say I choose this spin packet, normalize the intensity to 1, and then sweep the pump frequency. As we change the pump frequency, and when the pump frequency matches the probe, there will be a dip in the intensity. It will no longer be like the Boltzmann intensity, it will go down because we saturated some of the electron spins when the pump reaches the probe frequency. So this is what will happen if the coupling is weak or if the spins are dilute. So we will only see saturation of the electron spins. In the case of strong coupling, we observed something very surprising. Like initially, we didn't really understand what was happening, but we did similar experiment. We chose a spin packet and we swept the pump frequency across that spin packet. In the dilute case, we only saw saturation. Here, in addition to saturation, we see these two humps. And these humps, they cannot be explained using a single electron if the spin system is diluted. These are possible only if we consider strong coupling between electron spins. So these humps, they are, after analyzing it for a year or two, we think these humps are actually coming from the dipolar order, which is being generated by the pump pulse. And these humps would be there if the coupling is strong. So to understand why it's coming from dipolar order, I will show you a simple analysis based on density matrix. So in all our experiment, normally the initial density matrix is considered to be thermalized with the Hamiltonian we have. And in our Hamiltonian at high field, we basically have the strongest thing is Zeeman interaction. And for that, the most dominant term of the density matrix would be this Zeeman polarization and two spin polarization. But then this factor, the dipolar two spin factor, is squared. So if this number, if the polarization is weak, which is the case in our experimental condition at around 20 Kelvin. So this is around 0.1. So this factor is around 0.01. So it's much less, and we can initially ignore the two spin order. So this is our initial condition. We just have Zeeman order. And if you look at the density matrix term of Zeeman order and compare it with that of two spin order, they are very similar and they can be interconverted if we can selectively flip one of the manifolds. So if you just flip the first two unit or the last two unit blocks, then you can go from Zeeman order to dipolar order. So a Zeeman order on a single electron spin can be converted into dipolar order of two spins. So this is possible with selective pulse. Now, suppose to further extend this and to show some numerical simulation, say we have two spins and they are coupled. So you get two doublets, one for each spin. If we mimic our Eldor experiment, what we did in Eldor was we swept the pump pulse across the EPR line. So if you do that and monitor how does the Zeeman order polarization, basically this term changes as the pump pulse is swept. When the pump, and if we do it with a very low power pump, as the pump matches one of these resonances, we are saturating that transition and there will be a dip in the Zeeman order. So we have 4 dips in the Zeeman order, one for each transition. Simultaneously, if you calculate the two spin order, the longitudinal Zeeman order, dipolar order, you see at these conditions where you saturated the Zeeman order, a dipolar order is generated. And it has a phase, it could be positive or negative depending on which of these two manifolds you saturate. So this is with low power. If you do a more broad banded saturation, the Zeeman order is saturated even more. It's like even at some offset, you have saturation effect. But since this dipolar order, it has positive and negative phase, if we do a more broad banded saturation, we attenuate the creation of dipolar order. We can create some dipolar order only if you go to some off resonance condition, because at that condition, the saturation of these two manifold would not be equal. They would be unequal. So effectively, there is a net saturation. So you get a positive or negative dipolar order at the offset. And this is what is actually seems to be happening in our experiment. So in our pump probe experiment, we can change either the power of this saturation pulse or the length of saturation pulse. If we do a more effective saturation, we see that these humps, they go further and further. So the saturation becomes more non-selective, and the dipolar order that we generate, these humps that we generate, they become lower in magnitude. And the Zeeman order becomes higher in saturation of Zeeman order becomes higher in magnitude. So it seems that these humps, they are indeed based on some simple analysis I showed you. It seems that these humps are a resultant of dipolar order that we generate, and that is being generated between coupled electron spins. Okay. Another proof to show that these humps, there is in whatever EPR we are recording, there are two kinds of spin orders. To prove that, we can do a relaxation experiment. After creating the dipolar, so with the pump, we create some dipolar order and we saturate the Zeeman order. We can do an experiment where we vary the delay, where we have a variable delay before we actually acquire the individual components. And if these two are of different orders, then the relaxation would most likely be different. The rate of relaxation would be different. And in fact, it is true. So if we saturate and have a very short delay of 1 microsecond, so we see dipolar order generated and Zeeman order saturated. But as we increase the delay, we see that the saturation of Zeeman orders, it is nullified. So there is a fast relaxation of the Zeeman order, but the dipolar order which is generated, it remains there. It decays very slowly. And because these operators, they have different symmetry, so it makes sense that their relaxation might also be of different rate. So this is another additional proof that we are creating orders, two spin order between coupled electron spins. And indeed, if I can now come back to BDPA, for both BDPA and sulfonated BDPA, we see these strong humps. And these humps could mean that there is strong coupling between two BDPA molecules. Only then these humps are being generated, which in turn means that the DNP that we see in BDPA is not DNP of one electron. It's DNP of multi-coupled stacked BDPA. Okay, now I would like to summarize what I told you so far. So I hope that I convinced you that in DNP there remains many challenges, especially when it comes to DNP of many electron spins. It's not well understood. And EPR is a very useful tool to understand those effects, because the source of DNP is electron spin. So if we can measure electron spin, we can get some insight into DNP and know like whether the DNP is coming from, say, one electron or multiple electron. You can do experiments like pump probe, and that can help us to know about the coupling network present in our DNP system. And in particular, I showed that there could be humps, and those humps would be signature of many electron spins coupled in our system. I think this experiment is useful also for many other fields, like for quantum information science, where people are trying to develop spin qubits, electron spin qubits. So having an access to analyze multi-coupled electron spin would be useful for some other research also. I'm very happy. I'll be very happy to take any question. Before that, I want to acknowledge Songi Han, with whom I did all these research, and also the graduate students, Celeste, Raj, and Khan, who have been leading these projects. So I'm very happy to take any question now. Before I do that, let me actually advertise about NYU Abu Dhabi. So right now, NYU Abu Dhabi is my home, and this is how the institute looks like. It's located on a small island in UAE, and it has great research infrastructure. At present, we have a 600 megahertz solid state and also a solution state NMR, a DNP, we have pulsed EPR, we have continuous wave EPR, we have even clinical MRI, benchtop MRI, and a 3-qubit based quantum computer. So it's a really great place. I hope you can visit this place at some point of time. All right.
Thanks, Asif, for this nice talk. And yeah, I think the floor is open for questions. So since the crowd is quite small, I would suggest that if you have a question, you just unmute yourself and you can speak out loud. I would actually like to start with some questions. First of all, maybe what is the field of the pulse EPR you have now?
Where?
Yeah, at Abu Dhabi. Yeah, just
Abu Dhabi, it's just commissioned. It will be an X-band pulse EPR.
X-band pulse. Okay. So you can do the same experiment at X-band. Do you think that doing pulse EPR Eldor, so pulse Eldor on this system would answer the questions about DNP mechanism? I
don't really think it would be very helpful, but then because at X-band, many of the interactions are non-secular. The coupling is a lot larger than the nuclear alarm frequency for many radicals. So we are not in the high field limit under which DNP experiments are done. But then pulsed EPR can have some other utility. We can use DNP not just for signal enhancement, but also to study electron spin about electron spin, which would be useful for, say, in solar energy research. Like there is a process called singlet fusion, and that's basically we generate with light, we generate two triplets. And knowing the electron spin dynamics for those two triplets is a very important research topic. So we can use DNP for those kind of studies. But I don't think developing pulse DNP at X band, I don't know if that would translate really to high field.
Okay, thanks. I have a few more technical questions, but maybe I see other questions. So Yuya, you want to go ahead?
Yeah. Excellent talk, Asif. Very nice presentation. So I have a few questions. First one is for the thermal mixing DNP, do you think is it only the dominant effect for the narrow line polarizers, or you think it could also happen with, for example, nitroxide, where the line becomes much broader and your electrons at the same frequency will be less than what you have with, I don't know, trito or other things?
I think it might also happen for broad EPR line, for example, nitroxide. And there are some studies which shows thermal mixing DNP for nitroxide. The only thing is in tritle BDPA narrow line, it's very easily distinguishable because it cannot be the very basic cross effect. Whereas in nitroxide, it could be solid effect, cross effect. They have very broad DNP profile. So distinguishing a multi-electron effect DNP in those systems is more challenging, but I think it's present even there.
Yeah, and another question is on the page 11. So you showed this deuteration effect. I think the yeah. So on the left-hand side, the bottom plot here, so it shows the DNP enhancement, but I say it's just plus minus 1. So is it a normalized plot, or is why the enhancement becomes much smaller compared with the protonated one?
It is normalized. So, but also in the case of deuterated, it is low because now the enhancement is most likely happening to a more far off nuclear spin. So the hyperfine coupling is reduced. So that could be a reason why the overall enhancement is low. But I think this I normalized to -1, and I took it from paper. So, but it is low. Indeed, it is low.
Is there a value, like how much is the enhancement in this case?
I think the enhancement is around 4 or 5, something like that.
Okay.
Compared to around 70 or 80 for fully protonated system.
Okay, and the last question is, you had this pump probe experiment thing. So how fast do you scan over the EPR line? So how long do you pump at each of the frequency?
So that we vary. So for instance, in the experiment I showed here, so here like but at least since the microwave power is very low, and we rely a lot on spectral diffusion to have a big saturation. So normally it's at least around a few tenths of microsecond. If we do like 1 microsecond, we'd hardly see any effect. But then we can also go to like hundreds of milliseconds. So we vary the length of pump pulse.
And you just pump the pulse once instead of repeat it several times before you move to the next frequency. Is that right?
We are already in a regime of, we are already in non-coherent regime. So whether you saturate and give a delay and then saturate again, it will not make a difference because we are not effectively doing a nutation.
Yeah.
Okay, now maybe we go to other questions, to other people.
Thank you very much. Thanks.
So Ilya, it's your turn.
Hey, Asif, congratulations on the appointment.
Thank you.
Very, very nice. You are, of course, completely right, is that these distances, less than 20 angstroms or so, DEAR doesn't work. But the reason it doesn't work is that at these distances, the inter-electron coupling is in fact dominated by exchange interaction. which rapidly becomes stronger than the dipole-dipole interaction. And below, 15 angstroms or so, it actually dominates. And so when the two frequencies of your electrons are somewhat different, of course, your two spin order, what you call dipolar order, will be generated not just by the dipolar interaction, but also by the exchange coupling. And in fact, for certain orientations, if they're at the magic angle, it will only be generated by the exchange coupling. Are you certain in your theoretical treatment? I mean, mathematically, these are very similar processes, right? Except there's like a plus in front of a flip-flop versus a minus for the two interactions. How certain are you that this is not in fact predominantly the exchange that's generating the two spin order?
You mean, so I think most likely it is both exchange and the secular dipolar term. Like the net dipolar order is being generated, but for the simplicity, because there will be exchange depends on how far I take the two electrons, whereas this order would not depend on how far they are taken. So for simplicity, this model only involves the secular dipolar term, not the full. But in reality, I think exchange is playing a role. But it's
actually very easy to accommodate in your model. You just, so in the dipole secular, the coefficients between ZZ and the flip-flop are fixed. They simply stop being fixed because exchange adds and subtracts differently from the two parts. It's very easy to extend. It's just, you see, at some distances, exchange would be wildly dominant because it depends so strongly on the distance.
Yeah, I think I would try to do that. And if some help is needed, I'll get back to you.
But awesome work. Thank you.
Thank you.
Okay, now we go to the second Ilya Kaminker. If you want, you can unmute yourself.
Yeah, hi. Very nice, Asif. Hi, Asif.
Hi, Ilya.
Yeah, I'm actually curious about the BDPA spectra, because I also saw it in your paper. It looks like when it becomes at high concentrations, when you measure the spectra at high field, it becomes asymmetric.
Yes.
Any idea what's going on there?
I do not understand the shape of the EPR line. All I see is that it's way broader than what one would see just from G anisotropy. And it also changes. It seems like there are multiple components there, because when I change the delay between two detection pulse, then the spectrum changes. So it's being weighted by the relaxation. But I do not fully understand like how to model that kind of EPR.
Gentlemen, it's a cross correlation. These are known effects, so differential line widths. So if you type cross correlation, there are two of them, G hyperfine and hyperfine, and that's what's causing this.
Oh, okay. I will look into that. But I didn't try to model that, Ilya.
No, I understand. I was just curious about
there's only one package that can model that, Asif, and I think you can guess which.
Yeah, I know it's not spin evolution, it's spinach.
Of course it is.
Yeah, I have actually another question. So for like how many electrons you think are actually involved in this stuff? Because like in your paper, you can model most of them with like 3 electrons, I think, right? But if you go back to like classical thermal mixing theory, like Goldman and stuff, they basically assume all electrons are talking to each other.
Yeah.
So experimentally, what do you think is closer to reality? Is it small clusters with like countable number of electron spins, or is that at some point becomes like a total real bulk effect?
Honestly speaking, I do not know the answer, but 3 is the minimum. Less than 3, we can't do it. But if it is higher, I think definitely whatever profile we are getting, it would be more robust and smoother. So I do not know the answer, but also it becomes very challenging. Like going from 3 to 4 is like exponentially harder. So I think again, spinach might be a thing to use. But right now, for me, even doing a 3-spin simulation, it takes at least a couple of days if I do without too much of approximation. So, but I think, yeah, if we have like, it also depends on the strength of interaction, because if the interaction becomes larger, then we need more number of spins in general. So I don't have a good answer, but the plan is to go from 3 to 4 electron spins and see how does these profile change.
Okay, thanks a lot.
Okay, then we have one last question from Natalie.
Hi, Asif. Very nice talk. Thank you. Very interesting results on the water-soluble BDPA. Could you give a little bit more information maybe about your sample concentration and the microwave power used? Because even at 70 Kelvin, these results are quite different, right, than what Cody published in 2014 on SA-BDPA at 100 Kelvin, where this was an absorptive enhancement even at 40 millimolar. So can you comment on that a bit?
Yes. So unlike what Cody did, it was with gyrotron, right? So a lot more power than what we are using with solid state source. So definitely
a solid state source.
So I'm saying like the power here is a lot less. In our case, the power is around, at the source, the power is around 300 milliwatt.
Okay.
But how much of power reaches at the sample position, that we are not sure, but say it could be like around 200 milliwatt if everything is optimized well. But one thing is sure, like if we go to lower temperature, it becomes more dispersive. And also if we have lower power, even then it's more dispersive. And you can think that if you use a lot of power, then some of these positive and negative, they self-cancel. So because of larger spectral diffusion at higher power. So it could be the reason like why at 90 Kelvin or 80 Kelvin with gyrotron, more power, you didn't see the dispersive profile. So that is my guess. Does it make sense?
Yeah, what's your sample concentration here?
Sample concentration is around 40 millimolar. But
did you try that with standard BDPA and see similar temperature dependence, or do you have results for that?
For standard BDPA, I don't have under MS, I don't have this temperature dependent profile for standard BDPA.
Okay, great, thank you.
Okay, I have one last question actually. What is the role of the sample preparation procedure? You talk a lot about aggregation. Can you reproduce these aggregates? Are always there? What's your comment on that?
I think sample preparation is very important. Like for instance, if we read this paper by Thomas Frisner,
exactly,
they reproduce this several times, and sometimes they don't see this central feature.
Yeah.
So I do think sample preparation is very important. But what I show here is, this is like almost reproduced 5 or 6 times. So this effect is real, but how you prepare your sample, how you do your experiment, like what's the time between sample preparation and measurement, those things would change the enhancement number, but not much the profile.
Okay, that's clear. Okay, if there are no other questions, I think we can close the session.
I have another
today.
one.
Oh yeah, sorry. Yeah, just
Sorry.
go ahead.
Yeah, so I have some comments on the distorted BDPA EPR line or the distorted crystal line. So there might be some components where it has very fast relaxation. For example, if you are talking about 40 millimolar here, so there might be the instantaneous diffusion effect, which the time scale will be tens of nanoseconds. And if you're using the Euro echo detected field sweep or to mirror the line, so you will miss this part. And there's a way to avoid that. So if you just, instead of using 2 pulses, if you use 1 long pulse with smaller amplitude, So, and if you detect the FID from that, so you can just avoid this effect. And if you do the same and see whether the line is still distorted or not, that may give you some indication whether it's an aggregation or it's just a fast relaxation thing.
Yeah, I think it's a good comment. Normally, to know whether or not there is instantaneous diffusion, we do that variable length experiment. But even then, we do not change the, I'm not showing you the EPR profile here. These are DNP profiles. But this is, for instance, the DNP profile, which is enhancement as a function of pump frequency. But the EPR, yeah, to check.
Yeah, it's the plot where you show this asymmetrical EPR line, the part there. Yeah.
I think I showed it somewhere on the top of one of the Eldor profile. Like this one. Right?
Yeah, yeah.
So yes, like from varying the length of pulse, it does change, but it still remains asymmetric. So a lot of it is also caused by the dipolar broadening of the tritol radical. So the broadening remains there. The asymmetric shape remains there.
But if you, instead of using 2 pulses, if you use one single long pulse and just detect the FID, so that will fully eliminate the effect from the instantaneous diffusion.
Like how long, I'm not sure how long the pulses have to be, because our experiment is done with very low microwave power. So already to have close to a 90 flip, we use about 700, 800 nanosecond
Right,
pulse.
okay.
So these are already very long pulse. If we make it too longer, then it's almost of the same value as the TM of the electron spins. So we may not get any FID.
Okay.
Okay, now I guess we are done with the questions. So yeah, we close the session for today, and the next one will be on the first week of November. All right, so thanks, Asif, for your seminar. It was very nice. And yeah, good luck for your new position.
Thanks, Thomas. Thanks everyone for being here.
Bye-bye.
Bye.